Now we discuss what the requirements of a good watermark are and some advanced techniques to design digital watermark. First, a good watermark has to preserve the correct functionality of the intellectual property, because otherwise the watermarked IP fails to meet the design requirements and will have no value. Second, the design overhead introduced by the watermark must be negligible or very low. We know that the value of many intellectual properties are not only their functionalities, but also how these functionalities are implemented with high performance and low cost. High design overhead or performance degradation will reduce the value of the intellectual property. Third, the watermark has to provide high credibility of the authorship, or the probability of coincidence that others will implement identical IPs should be low. Next, the embedded watermark should be easy to detect as the proof of the authorship. However, it must also be resilient in the sense that it will be difficult or impossible for an adversary to remove or modify the author's watermark. Transparency means that the addition of watermark and its detection should be transparent to existing design tools and design softwares. Otherwise, it will be difficult for the watermarking scheme to be adopted. Ideally, a good watermark can also be used to protect specific parts of the design in addition to the entire design. This is important in the reuse-based design practice because IPs will be integrated and the designer may not be able to insert watermarks to all IPs. Finally, as we have seen before, a good watermark should be fair to all the designers or all the possible signatures. Next, we will use low overhead and easy detectability to demonstrate how these features can be achieved. The design overhead and the performance degradation caused by watermarking is unpredictable, and in many cases, they are also uncontrollable. This is due to the randomness of the additional design constraints based on the random watermark, and also the fact that most design tools contain non-deterministic algorithms. In addition, if we want to control the design overhead, the security of the watermark might be compromised. To solve this problem, we can use the two-phase zero overhead watermarking approach. In this approach, we first do the design without any watermark to obtain the best possible performance. Then, we identify places where we can embed watermark without introducing performance degradation. Next, we embed the watermark, and then we redo the design to obtain a watermarked intellectual property. This slide shows how we can apply this strategy to FPGA design. In FPGA design, we start by reading the design constraint files and then do a synthesis, and then do the place and route. And the last step is to generate the configuration bitstream file. If we try to embed a zero overhead watermark, what we do is we follow the first three steps, and however, we're not going to generate the configuration bitstream file right away. What we do is we try to extract timing information on certain passes from the place and route result. And we'll combine this with the author's signature to use the author's signature to modify the delay information on these certain nets. And then we do the place and route again. And then we check whether the timing requirements are satisfied or not. If they are not, we come back and potentially we may have to reselect nets and then do the place and route again until all the timing constraints are satisfied. And then we generate the configuration bitstream file. So what we see here is because we are checking the timing constraints are satisfied or not, so there shouldn't be any timing degradation. And also, we are going to show later on using the industrial benchmarks to see whether there's any resource overhead. The only thing we can see here is we have to do this step multiple times to meet the timing requirement and embed the user's signature. And we'll also show you by results to see how much this additional time will cost. So this is an example watermarking scheme. So what we do is after we finish the optimal design, we try to select non-critical passes. So for example, the first column shows the starting flip-flop, and then the second column shows the destination flip-flop. And then the third column shows the delay in the optimal design from this source flip-flop to the destination flip-flop. And none of these delay are critical in the sense that the critical delay are all shorter than these delay constraints. So for us to embed watermark, what we do is we try to modify the last digit of these delay constraints. For example, if these are the watermarking bits we want to embed into the FPGA design, what we do is we replace the last bit by the watermarking bit to obtain a constrained delay profile. And then we use this as the additional constraint to the original problem, trying to do the place and route again. As a result, we have seen this result here. So these are the 4 industrial FPGA design benchmarks, and this column shows the resource requirement in terms of the number of FPGA slices, and we see the original one and the watermark design. In all the cases, the required slices for the original design are the same as the watermark design, which shows that there is no resource overhead. And the second row for each benchmark shows the timing requirement for each application. And a check mark means here we have satisfied the timing requirement. So in all the cases, the timing requirement or the performance are met. There's again no overhead. And finally, we mentioned that there's a design time overhead to do the place and route again and again. And in all these cases, the time to do that is in seconds. Finally, we want to show that this gives us a very strong proof of authorship. And this is measured by the harming distance of the configuration bit stream file of the original one and the watermark design. And this shows the harming distance in percentage, 1.09% up to 4%. And pay attention that for these benchmarks, the configuration bitstream files are in terms of megabytes. So even 1% is a lot of difference between the two designs. So that can be used as a very strong proof of the authorship. Next, we discuss the detectability problem of the watermark. We have seen these slides before. So it shows the basic concept of the steganography system and also the constraint-based watermarking system as an example of the steganography system, where we embed the author's signature in the steganol problem using additional constraints to the original problem. However, the problem in this approach is how can we detect the embedded watermark and use it to prove the authorship. The public watermark approach solves this problem. In this approach, instead of hide the author's signature everywhere in the original problem, we select certain places and then embed watermark only on those certain places. So we will highlight how do we solve several problems in the following slides. Question number 1, how we can embed the signature. Number 2, how to detect the signature. How much do we lose by doing this, and how much can the attackers gain by knowing this public watermark. We first use the graph partitioning problem to show the basic ideas behind the public watermarking. In this problem, we have a graph and we want to partition the vertices in the graph into two disjoint subsets such that the subsets are balanced, and also the connections between the subsets will be minimized. For example, here is a partition that cuts the graph into the top half and the bottom half. For this partition, it is perfectly balanced because there are exactly 12 nodes on the top half and also 12 nodes on the bottom half. And also when we count, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 edges has been cut, which means the connection between the two subsets are 10. It is not easy to find a very good solution for graph partitioning problem. So indeed, this graph partitioning problem is also an NP-complete problem. This slide shows how we can embed public watermarks. First, we make the following information public. The 8 pairs of nodes, as shown here, a pair of 0, 0, a pair of 1, 1, all the way to a pair of 7 and 7. And second, the scheme we use to embed public watermark. If we want to embed a bit 0, we keep the pair of nodes in the same subset. If we want to embed a 1, we keep the pair of nodes in different subsets. For example, if we want to embed a capital letter O, what we do is, let's assume that we encode O in ASCII code and put the parity bit. And what we do is, we first partition the 8 pairs following the public watermarking rules. For example, the leading bit is 0, which means that the 2 7s will be in the same subset. And the second bit is 1, which means the 2 6 will be on different subset. And then we partition the rest of the node, and then we get a partition like this. So if we do the partitioning this way, now everyone can detect the watermark and then verify it. That is why we call this one public watermark. Now we consider the security and detectability of public watermark. The public signature will be encoded in ASCII and then embedded into the problem using a scheme that is known to the public. Therefore, it is very easy for the attacker to come and modify the watermark. For example, he can change one of the bits and then to completely remove the watermark or modify it to another watermark. To solve this problem, we can use some crypto primitives. So for example, we can hash the bitstream file and then encrypt the hash using the bitstream itself as the key. And in this way, we can have the public watermark into two parts, which the first one we call the public watermark header, which is the plaintext or ASCII code of the public signature. And then we have a much longer watermark body, which is being encrypted and encrypted of the hash. And this is the entire thing will form the public watermark. Now with this new public watermark, the attacker's job becomes much more difficult. Why? What we see here is, it is still easy for the attacker to modify the public watermark header. And however, because of randomness involved here, even if the attacker changes only one bit or a few bits in the public watermark header, relatively half of the bits in the public watermark body will have to be changed. And then this makes the attacker's job much more difficult, even if he knows where to change all these bits. And finally, once we do all this, how difficult it is to verify or authenticate the watermark. We claim this is also very easy. So for a person to verify the claimed public watermark, he or she can start with the public signature, do a plaintext ASCII encoding, and then check the public watermark header. If the header matches, that is a very good sign that this is probably the authenticated user. And if the user wants further verification, she can also hash the bitstream file from the public signature and then use this as the key to encrypt the hash and then find out what is the body of the public watermark, and then go to the design to verify whether the public watermark body has been changed or not, and then eventually verify or detect the public watermark.